Hello, this is Dr. Kozhanov, and that's online lecture 7. So, what we will do in this lecture is we will continue with magnetization dynamics. And if you have time left, we'll talk about spin torque device applications. So, I would encourage you to review the previous lecture. There are a couple of things that we learned. One of the important things is the uh, Landau-Lifshitz equation, and Landau-Lifshitz equation can be written this way: minus gamma m cross b. So this is vector, this is vector, this is vector. So what this um, equation implies that if you place magnetic moment, well, I use capital M for magnetization, implying this is a magnetic moment of a unit volume. So if you'll place a magnetic moment in presence of magnetic field, that's supposed to be a straight line, what will happen is that it will start precessing. And the way how it moves in presence of magnetic field is described by this Landau-Lifshitz equation. If you solve this equation for m as a vector, uh, that solution m as a function of time, you should get precession. So if this is our coordinate axis, this is z, x, y, then if you look at this magnetic moment in x, y plane, so z points upward, this is like looking from the top in the field, then you will see that it precesses. So if it's a free um, magnetic field, if it's a just magnetic field in free space, it will be a circular or a circular line. It would be a circle, so it would be sine wave along x and y axis. So magnetic field points up here towards you out of your screen, so therefore the precession is going this way. So it will precess. Now, this is number one. Number two is we looked at this equation and said that, okay, we are not interested in big oscillations of magnetizations and switching. We're looking for small oscillations. So what we say is that, okay, our magnetization is almost always fixed along the y-axis, but there is a small perturbation, time-dependent perturbation of it. So basically, it stays always up, but it wiggles a little bit left and right. Not left and right, but it basically precesses. But this precession, so m naught is this length, and small m is that. So it is a small additive. Then this small m can be represented as an oscillation, so it's some m naught I omega t. We are looking at oscillations at a certain frequency, and in order to make it oscillate, our magnetic field B, we can say B, but I used H last time probably, is B naught small b is a function of time. You can convert it to h by dividing by mu naught, and that small b as a function of time was also b naught e I omega t. So what we are doing is we are wiggling this magnetic moment with a small magnetic field, and we are looking for the response at the same frequency. So if we shake it with frequency of omega, we are looking for the response at the same frequency. So that was our approach last time, and the important part that we concluded is, first of all, we can link our magnetization and H, and you already know that, chi H. We didn't use vectors before, but now we are using vectors, and we link it with therefore we use susceptibility tensor. So susceptibility tensor is, in this case, dependent on frequency. So how our material will respond to magnetic field depends on frequency. It depends on the susceptibility value, and susceptibility uh, itself, it's a tensor, so there are four terms here. You can look it up in the previous lecture. But this susceptibility, all of these terms are dependent on magnetization and on magnetic field. Let me use H again. And there is also a resonant frequency omega naught. So again, I encourage you to look in the previous lecture. So what it means is that if you remember what susceptibility is, so the illustrative, this is not dynamics, this is statics. But if you apply H and look at the magnetization, we can have diamagnet, we can have paramagnet, and we can have ferromagnet or ferrimagnet. So there are different magnets we learned, but you see the ratio, let's say M at the same magnetic field, you can have various level of magnetization that would correspond to low and high levels of susceptibility. So if we plot our susceptibility terms as a function of frequency, and let's say we are working with a ferromagnetic material, then there would be certain frequency at which it would be big. So we'll start with something reasonable, and then there would be a peak, and then it would die out to 0. So this is, by the way, it's the shape of this curve is not quite right what I draw, but the main idea is that there is this resonant frequency, and that is resonant frequency at which all magnetic moments in the material, whatever shape of it is, so all magnetic moments would oscillate at the same time, which means that if you have magnetic moment here and this is your material, and you have magnetic moment there, there, and there, all of them would oscillate. So if this tilts this way, all of them will tilt that way simultaneously. So this is called a ferromagnetic resonance, FMR. Now, if you are doing low frequency, your system follows the field, and as you approach the resonant frequency, it raises up and reaches the peak where all of them oscillate at the same time, and that's a resonant frequency for all of them. And then as you go to high frequency, they cannot oscillate that fast, and therefore your oscillation amplitude dies out to 0, and that's reflected in susceptibility. Other important part to understand is that this susceptibility is dependent on the shape of material. It's not only dependent. If you take infinite material, then yes, but no, it would be independent. But we don't have infinite dimensions of materials. So basically, there were two sections in last lecture. One, we just looked at the magnetic moment in presence of magnetic field, but then the other one, we took our material with a certain demagnetization factors. And I think I used Nx, Ny, and Z to represent demagnetization factors along different directions. So if we would take a sphere, then for a sphere, this Nx is the same as Ny, the same as Nz, and the resonant frequency then would be gamma B, where gamma is a geomagnetic ratio. B is a magnetic field. Well, I have to take B naught. And this is the ferromagnetic resonance for the sphere. But what we can do is we can take a very thin plate. So this is continuous, this is new. So what we take is we take a flat plate. Flat plate, something like this, very thin. Now we apply B at 90 degrees to the plane. Then demagnetization vector, so that's a z field, x and y in plane. So nx is the same as ny is 0, and z is 4 pi. That's CGS. These are demagnetization factors. And then if you use this for our calculations that we did in the previous lecture, you will see that the resonant frequency would be equal to gamma b minus 4 pi m. And that's CGS. You can use SI units for the same, then the difference would be, it's the same gamma b, but as always in SI there is mu naught instead of 4 pi m in SI units. This is b perpendicular to the plane. But the interesting part is that if you rotate b and make it in plane, so let me rotate it with a different color. So for this b, in plane b, your in plane resonant would be different. That would be gamma b naught plus. I'll use SI units m here. So you see, it is the way how our system reacts to the field and how these magnetic moments want to oscillate depends on the direction along which you apply the magnetic field if you work with different shapes. Now, that was the oscillations. Now, what we did is, if I go back here, and that is something that you did last time. Let me highlight it. So this and this. So the important part here is this. You see, there is only time dependence. So it is just oscillations. It's not a wave. And we apply field as oscillations. Now, this problem can be made a bit more complex. As always, we can make things more complex. So instead of using standard oscillations, what we can do is how do we make it more complex? We still can apply magnetic field, the small portions of magnetic field as H naught E is I omega t. So we are just, if you have a material, you apply magnetic field, big magnetic field, H naught, but at the same time you apply the wiggling H at a certain direction. And what it does is that your H naught aligns your magnetization along the field. So you basically magnetize your material along the field direction. But this field, what it does, it pushes the magnetic moment left and right. It applies torque and it pushes left and right, and well, you know that it's a cross product there. So the torque is m cross b, right? So b has the same direction as h. So you magnetize it this way, but you are applying torque to this moment. So, and it starts wiggling left and right. So this is a magnetic field, but as similar to actually any waves, instead of looking for uniform oscillations where all magnetic moments oscillate at the same time, we can look for solution where your magnetization is has a wave part. So for the wave, we have the same, the amplitude, we have exponential part, then we can have I omega t, the oscillating part, but at the same time we'll need a parameter dependence. So what we'll do, we'll add kr. Now k, if you remember, k is a wave vector, 2 pi over the wavelength. In general, this vector, it's a vector, so we can say that there is a dot product there. And what we're looking at is that while we wiggle all of them at the same time, we allow our oscillations to um, spread out at a certain velocity. And you can look at the velocity. So in this case, what we will have is we will have waves of magnetization oscillations. So I'm not going to do the math. If you're interested, you can substitute that there with a k-vector, but then it might become pretty complex. So I would say that this is too advanced for the undergraduate course. But this is the way how we approached it. And although you are at the undergraduate level, you were able to look at the ferromagnetic resonance where we didn't have the wave part. By adding the wave part, again, it becomes a bit complex, but still we can look at what happens. So of course, applying everything, applying field to all material makes it a bit um, hard to analyze. So in the experiment, it would be way better if we would apply our magnetic field only a small portion of the material. Let's say you have this stripe magnetized along this direction, and you apply, and it is magnetized because this is M, because we apply H in this direction, and then we apply small h up and down to this area. So what we do, we wiggle magnetization up and down in this small area. What happens is that these magnetic moments in this area, in this area, they do not stay there. I mean, they interact with magnetic moments in the other portion of material. At the same time, the interaction does not spread instantaneously, so magnets interact stronger with magnetic moments in the area neighboring to this excitation area. So what happens is that, for example, I'm now looking at M small, or we can look at magnetic moments. So if in this area, um, they would be aligned along this direction. So if in this area we tilt magnetic moment this way, it interacts with magnetic moment here, and it also tilts it this way. And then we have this. Then after some time, what happens is that this magnetic moment here, this one, wiggles up and down, and that transfers to magnetic moments on the right. And at the end of the day, what we'll have is that we'll have magnetic moment pointing in different directions. And if you look at this, if you look at the directions at which the magnetic moment point, then M would be up, down, up, and down, and etc. So with respect to this line. So magnetic moments would be pointing up, down, but in the magnetic resonance, all of them would be pointing up at the same time. This would be FMR. But in this case, there is a certain wavelength associated to that. So if you look at this, that would be the wavelength. So if we change frequency, then the wavelength will increase and we will reach ferromagnetic resonance. So for ferromagnetic resonance, wavelength is infinite. Well, I should write approaching infinity, but for infinite wavelength, we have all magnetic moments moving up and down. For finite wavelength, we have a wave of magnetic oscillations propagating through the structure. So these waves are, and as you remember, we are in magnetostatics. Magnetostatics is the fact that we say that our magnetization is pointing in this direction and we look only at small oscillations. So therefore, these are called magnetostatic spin waves. So magnetostatic spin waves. And in many cases, this phenomenon of propagating wave of magnetization is just called a spin wave. I will abbreviate it with SW. So spin waves, and spin is, we are not referring to electron spin, so we are referring to magnetization oscillation. But there are spin waves in materials where you have electron spin, uh, density waves, and there are other phenomena. So I think that spin waves in this case use a spin that indicates the magnetic moment. So let me illustrate you this, just 1 second. So here is the YouTube video from uh, Graham Rowe part. It is a simulation of a single one line of magnetic moments. So here is one line of magnetic moments. So you may think that this is a line of atoms. And if you tilt one atom to the left, then this is what is happening. So this is a simulation. So you see each individual spin precesses. Each individual spin precesses, but they interact, and they want to be aligned ferromagnetically. So therefore, if this spin moves, that spin reacts, and you have this wave of uh, propagating magnetization oscillations. So this is the spin wave, and this is how it looks in um, one dimension. So now you can imagine that a similar thing happens in 2 dimensions and 3 dimensions, and of course it can be pretty complex. Okay, now going back to our oscillations and waves. So now the important part, when you study, for example, when you study light propagation, the important part is to know the velocity, and the speed of light, let's say, is a fundamental constant. Now for spin waves, it turns out that the velocity, and how do you get the speed of light? Well, if you plot frequency as a function of wave vector, then the slope of this curve would be your velocity, wave velocity. And in case of light, that is our c. And in general, velocity is our d omega dk, the slope of this curve. Now, this is for light. As you saw, we have spin waves. Now, if we would look at frequencies and amplitude, remember the ferromagnetic resonance amplitude, let's say chi, as a function of frequency. There was this resonance. Now, we have a resonance, and if we would go to higher frequency than the resonance, what would happen is that imagine that you have this material. At one frequency, you tilt all magnetic moments at the same time. And that is your infinite, I will draw it this way, infinite wavelength. Wavelength is much bigger than the size of the material, so that's a ferromagnetic resonance. Now imagine that now your wave fits within the material. So what happens is that you have magnetic moments tilting this way and then down. So you are, first of all, decreasing the wavelength. As you remember, k is 2 pi over lambda. So if you decrease the wavelength, that would increase the k vector. And second, it depends on the material, but in the bulk materials, usually increase of k vector means increase of the frequency. Increase in k vector, increase of the frequency. The straight line is just for the light, but we'll get there. So what happens that at high frequencies, magnetic moments do not want to oscillate uniformly at the same time, but there are certain frequencies at which they will start oscillate out of phase. So while this area of the material goes up, this area part of the material will go down, and therefore you have a wavelength, and all this will propagate in that direction. So what happens is then at higher frequencies, you will see the, let me use a different color, so you will have your ferromagnetic resonance, and then you'll have another resonance. That there is no circle. Another resonance, and another resonance, and another resonance, and more and more and more, and they're smaller and smaller. So what this thing means is that first of all, you have this omega naught here, and that is all magnetic moments oscillate at the same time. Followed by that, you have another standing wave. So of course, for the finite size of material, you cannot have a wave that propagates infinitely to that way. So the wave will propagate that way, it will bounce off this end of the material, and it will propagate back and interfere with itself, and you will form a standing wave. Standing wave where your magnetization oscillations will be, let's say for this, it would be very strong in this area and very strong in that area, and they will be out of phase. This goes up, this goes down. This is a standing wave, and that would correspond to this peak. This is standing wave, and you can relate that. So basically, you can fit. This is ferromagnetic resonance. Then you fit half wavelength, half wavelength, or quarter actually, one wavelength into the material, 2, 3, 4, etc. So, and you can enumerate this. So this is 0th mode, first mode, 1 wavelength, second mode, 2, 3, 4, half wavelength. We are counting half wavelengths, and etc. So if you have wave, it can fit a much certain length. Then within this same certain length, you can have 2 half wavelength. Then you can have 3 of them, 4, and etc. So, and all these standing waves in material would correspond to these peaks there. This phenomenon is related to spin waves, but it's a standing wave, so this is called spin wave resonance. And as we saw before in the previous lecture, but here again, frequency, this is an example, one of them, all of them actually, is proportional to the magnetic field. So you can see it here, you can see it here. This is b squared, and so frequency proportional to b. And there is also will be product of b naught m. We can look at it in the sphere. Here you can see there is a dependence on the field. So idea, and I mentioned that last time, let me scroll to the resonant curve. Yes. So as you increase magnetic field, your resonance moves to the right. So that leads us to experimental detection of ferromagnetic resonance. So there are two ways. One is you can take the material, place it in permanent magnetic field, apply wiggling magnetic field H as a function of frequency, and measure susceptibility, basically measure the magnitude of oscillations. You measure susceptibility as a function of frequency. So you start wiggling it slowly and then increase, and do very fast, and measure susceptibility at different frequencies, and you will get that peak. And you also can measure it at different H, and you will get different curves. Let me use different colors. No, different colors, yes. Typically, when you go to higher fields, magnetic field holds magnetic moments stronger, and the oscillation amplitude decreases. So in general, the amplitude decreases and frequency shifts to higher frequencies. You can relate it to a pendulum. So if you have a pendulum, in presence of gravity. Gravity points that way. Um, then frequency, or yeah, let's take frequency. Square root of what is it? L over G? No, G over L. Let me check. G or L. Dimensionality. It's square root of meter per second square times meter second square. Meter goes away, and that's 1 over the second. Yes, that's right. So frequency of pendulum is square root of G over L. And imagine that you can change G by placing this pendulum on the Earth's surface, on the Moon, or on heavy planet. And by changing G, stronger the G, higher the G, faster the oscillations. This is same happening here. Higher the magnetic field, higher the resonance frequency. Same here. Higher G, higher resonance frequency. So there is analogy. We actually did spinning top analogy there. Now the other part, I will erase this. You know this really, really, really well. The other way is to instead of let me get my pen back. Other possibility is instead of changing the frequency of magnetic field, what we can do is we can fix frequency. So fix omega. When we fix omega, it means that it fixes the frequency. Let's say we fix the frequency. Imagine that we are measuring at this particular omega 1. Fix omega 1. So we fix the frequency to this particular value. And if our field is weak, then our resonance is below this particular frequency. So now what we can do is we can plot susceptibility measured at these conditions as a function of big H. So if H is very small, then our resonance is below this frequency at which we are measuring. And that means that if the field is small, there is no resonance at our frequency. But as we increase the field, H increases, this resonance moves to the right, and at a certain point it will reach our frequency. So what would happen is that it will reach the frequency at which we are measuring, and then it would move to the right. Actually, this is not quite right, but this is very close. We are let me redraw this curve. We are moving from the other end. So we will start with this right end. So we'll start at certain value. We will move up, reach resonance, and then move down. So instead of having a resonant frequency, we will move the frequency of resonance to the measurement frequency with the magnetic field. So that would be our omega, but it's actually the h-axis, so that would be h naught. And if it is a sphere, as you remember, omega naught is gamma b, so gamma mu naught h. So the resonant frequency depends linearly actually for a sphere on the magnetic field. And by changing magnetic field, we can get our resonant frequency at h naught. So that is what is typically used in experiments. So imagine you want to measure ferromagnetic resonance of this material. So what you need to do is the following. First of all, you need to magnetize it along a certain direction. So you magnetize it, so you put it in the electromagnet poles. So this is one electromagnet pole, is the other. Let me use some color for shading. So this is our electromagnet. This is two poles. So these two electromagnets, what they do is they apply magnetic field no, this is not straight. Let me try better. They apply the magnetic field, in this case vertically H, and they're used to magnetize this material. So this is M. Now we need to wiggle it left and right. So basically we need to apply a magnetic field in this direction, and that should be a small, very small oscillating magnetic field. So what we can do, how do we apply magnetic field? Well, there are two ways to do that. One, and it is a pretty common way to do it, is to make another magnet. So basically what you can do is you can put another magnet here, electromagnet. I will designate it north-south, but you should understand that this is not north, it's an electromagnet, and more than that. This can be northeast-south and vice versa, and more than that, this magnet would apply our small h. Now, besides that, we also need to measure. Now, we can wiggle it, so we apply this for big H, and this one, let me use different color, quite aggressive color. We use this magnet for small h, for h, that would apply. But we also need to measure this, and here comes an interesting part. So if you look at frequencies at which these oscillations are happening, so let's calculate that frequency. So gamma 28 gigahertz per Tesla. B, let's take a very modest magnetic field. Let's say if it would be 100 Gauss, something really easily achievable, or let's do 1000 Gauss. 1000 Gauss is 0.1 Tesla. Mu naught 4 pi times 10 to the negative 7. So if you put these together, or we can use CGS units. So the beauty of CGS units, we don't need that. For CGS units, omega would be gamma B, and B. Let's do this. Gamma B, gamma 4 pi, gamma H. Or we can use, let's do this in Teslas. We don't need this. So 28 times 0.1, this is gigahertz per Tesla. Gigahertz per Tesla. 0.1 Tesla. 2.8 gigahertz. So if you remember, that is 2.8 giga, mega, kilo, hertz. I probably shouldn't do that. You're advanced enough not to explain you that, but this is fairly high frequency. So if you look at the spectrum, then you will see that radio frequencies are 2 megahertz, and gigahertz is microwave. So it's imagine that when you make a magnet, you have to wind a coil, and you have to wiggle that coil at these frequencies. So 2.8 gigahertz is a fairly modest frequency. This is for the spherical particle. So in general, and also that depends on magnetization. So if you scroll up, if you go back here, yes, here is a flat plane. So if you take a thin film, then you'll see higher the magnetization, in this case lower the frequency. If you're measuring out of plane, if you're measuring it in plane, higher magnetization, higher the frequency. So materials with high magnetization like iron and similar have fairly high frequencies, and it depends on the shape, on the material. So for ferromagnetic resonance, the inductance of this coil won't allow us to wiggle magnetic field that fast. So therefore, we cannot use electromagnet. What we need to do is we need to use a coil without having internal parts, so it would react fairly fast. And in these cases, even a coil wouldn't be very helpful. So we are going to use the following uh, setup. So we will have our electromagnet, big electromagnet, which produces horizontal field. We will put our material right here. And then instead of using wires, what we'll do is we will put it in the cavity. So cavity, it's a microwave cavity. So what is cavity is basically a box, and that box has certain standing electromagnetic waves. And if you calculate the wavelength for the wave of 2.8 gigahertz, so you will get a wavelength of in vacuum of um, about 10 centimeters. So 10 centimeters is what? 4 inches, right? So this is a reasonable size, and that is the wavelength of electromagnetic wave in a cavity. So it would be resonant, which means that in this case, you'll have oscillating electrical and magnetic field. And you can choose the geometry, so the electric or magnetic field of interest, actually we are interested in magnetic field, would oscillate in the right direction. So we make a cavity, and this is the big H. We will make a cavity in which the small h will oscillate up and down in this particular point. Now, why we choose a cavity? A cavity is basically allows us to get standing waves, and standing waves might get well controllable amplitude. So then, this is microwave cavity, so we should send microwaves in there. So that would be a waveguide. So if you go back in electricity and magnetism, you'll see that if you take a hollow square tube, a tube with a square cross section, or actually round might work as well, then you might have electromagnetic wave propagating. These are called waveguides. Waveguides. So you have to generate this. So this is generator. You generate wavelength, you generate microwaves and send it there. Now, when you send microwaves, your material will, you can tune these frequencies a little bit, but what we are doing is we're at fixed omega. So we fix this frequency following this schematic. So we fix frequency and use magnetic field to shift resonance around. When we fix frequency, what it means is that we can choose the geometry of the waveguides for this particular frequency and particular wavelength, and we will send waves in there. So waves are going in there, and in this cavity they resonate. They force magnetization, so I will draw magnetization below here of this our material. So magnetization would be pointing this way, and it would oscillate up and down. So this is capital M, this is small m. M will oscillate at our frequency omega. So now if the frequency, if it's not a resonant frequency for this particular magnetic field that we apply, then oscillations would be very small. They would be very small. But as we hit resonance, so what happens in resonance is that you send certain energy with magnetic field, and in this case the energy is not absorbed, but at the resonance energy get converted into the motion of magnetic moments of our material. So what happens is that if you send waves in there, they will start to get absorbed. Now it's a standing wave inside the cavity, but here the wave goes there and then it returns. It's a wave, it reflects. So if there is no absorption happening here, the wave will return, and our goal is to measure that wave. So what we will do is we will here in this portion, we will put a circulator. Circulator is a element, I will draw it that way, which allows energy coming from this side to be going into this way, and the energy that comes back, the return wave, would not go back to this branch, but would rather will be redirected into this direction. And you put a detector here. Typically microwave diode is detected. So that is the setup. And what would happen is that you would be sending microwaves at certain frequency down, and then detecting the microwaves that are coming out into the detector. This detector would measure how much of energy that we send in is absorbed by the material. And if you plot the amplitude measured, microwave amplitude measured by the detector as a function of magnetic field, if there is no absorption, then all energy, or most of it, minus losses, should come back. So we'll get this. As we hit the resonance, the material start to absorb. Oops, let me draw it in a better way. The material start to absorb. It absorbs the energy, and then it goes back. So this is how the measurement of that. And of course, this is absorption. And if inverted, we would get basically what is happening in that place. Now in real life, the material, this is apparatus which is called ferromagnetic resonance spectroscopy. This is technique, ferromagnetic FMR spectroscopy. Now this technique can be used not only for ferromagnetic materials, because as you remember, we also have paramagnets. And paramagnets, when we apply magnetic field, they get magnetized. And when they get magnetized, then you can measure their magnetic properties. So for paramagnets, the technique is called electron paramagnetic resonance spectroscopy. So EPR, that's electron paramagnetic resonance. So I will show you a picture in a moment. So this is a photo of electron paramagnetic resonance spectrometer, and you may see something that you have seen in my laboratory when you visited it. I would, if there would be no quarantine at this point, we would go to the lab and I would show you this in the detail. There are a couple things that I would like you to notice. So first of all, we need magnetic field to magnetize the sample. And if it's a paramagnet, we need fairly large magnetic fields. Therefore, we need big magnets. So this is the electromagnet, coils around it, two magnet poles, and you can see that we can apply magnetic field in this area. Let me use the pen. So the magnetic field here is in this or that direction. It doesn't really matter which direction it is. Now there is this box here. This box here. This box is called a microwave bridge because in real life the system is more complex than just this. So there is generator, circulator, it goes back, but the signal is very hard to detect. So instead of having the line coming back, what is typically done is the following. The microwaves are split into two. One portion goes here, there is this phase adjustment, and then it interferes with that. If they're in phase and dependent on the amplitude, there is zero coming to the detector. But when the signal gets absorbed, then the interference gets out of the balance, and you detect the signal. So I'm not going to go deep into the detail. I encourage you to look into that yourself, how it works if you're interested. But in general, this is a more complex microwave schematic. At the same time, so what we see here is this is microwave electronics right here, and it produces microwaves, and you can see that there is something going out, and this is the rectangular waveguide. So you have the microwaves going there. There is the circulator or something that allows to control it, and it goes into here and into the setup. This thing here, let me use a different color. This thing here, this is a cryostat. It allows measurements at different temperatures. Inside that cryostat, somewhere here where the sample is the cavity, a resonant cavity. Then it goes back through the same waveguide and into the measurement. And there are other microwave electronics that allows us controlling it. So the system you may see it's a bit more complex, but it is made for custom experiments. Now this image is basically showing us a cavity, resonant cavity, and you can see this is a rectangle. It looks like this. There is a microwaves coming in through this window. So if you look into that, microwaves are coming in along the x-axis right there. On the way to the microwaves, there is this iris. It's a small opening. This small opening allows to control how much of microwaves are coming in, and it allows us to better couple it. The reason why is that if you look at the cross section, this is how electric field looks like in the cavity. So the electric field comes in this way, and then there is a standing wave in there. This is the standing wave, and you have to control this entrance of microwaves to get the good standing waves in there, and you control with this screw. So basically you have a screw that you can move up and down, and that allows you to get more or less microwaves to come in and form the standing wave. Now corresponding to this electric field, there is the magnetic field in the cavity, and you can see that the maximum magnetic field, this is the sweet point here where you have this most dense magnetic field lines, and this is the point where you can apply magnetic field up and down. So what you do, this is a top view, and you can insert your sample from the top into the cavity and place it right in the middle here, and this middle would correspond to this sweet spot where the magnetic field is the most. Now, the paramagnetic resonance, as you remember, these paramagnets do not have spin. So if you look at the energy of atomic state, then energy of atomic state, if the field is zero, there is no difference between spin up and spin down states. But as we apply magnetic field B, what happens is that we have Zeeman splitting. So go back into the lectures, we talked about Zeeman splitting. So these energy levels split, and we have ms plus 1/2 here and minus 1/2 here states, and the energies go up and down, and the energy here would be 1/2 G factor Bohr magneton B and minus 1/2, and 1/2 is our spin ms G Bohr magneton B. So they split, and what happens is that we have this resonant, we have the transition between these two levels, and this delta E is equal to the difference between the two G Bohr magneton B. And if we shine microwaves at that particular delta E, if that is equal to h bar omega, and omega is the frequency of our microwaves. Then we should see absorption of the material. Basically, that is talking from the energy standpoint, but a we will have an oscillating spins. Now, that is typically what it is, and in a spectrum, because of the ways how it's most sensitive to measure, typically, uh, if you take a look at the resonance, if I scroll back up, this is an absorption resonance corresponding to the oscillation resonance, but typically it is a derivative that is taken of this value, and a typical spectrum would look like this. So you have derivative moving up, reaching the peak, and going down. So if you take derivative of the peak, you will get this. So if our peak looks like this is a resonant peak, then the derivative will look like that. And this is a typical uh, electron paramagnetic resonance spectroscopy, how it looks like. Now, where is it used? There are many different materials, and if you look at electron paramagnetic resonances, then you will see that you can study, for example, if you have molecule, in that molecule your electron has certain energy levels, and by measuring these resonances you can judge what are these energy levels are in paramagnetic materials. You can study electron nucleus interactions in these materials, because nuclei also have certain spin, and also you can study anisotropy of materials and many other things. So basically, if you have magnetic material, then you measure the resonance at which magnetization oscillates. If you have paramagnetic material, then you can induce magnetic moment by external magnetic field, and that allows you to measure that resonant frequency. So based on that, you can judge what bonds are formed in this material, what is this material made of, what groups, and more than that. So if you have certain material with a certain, I don't know, for example, you have the CH3 group in your organic material. This CH3 group, it has certain bonds, and for these certain bonds there is certain electronic structure of each atom, and they have certain resonances, which means that by measuring your material and measuring the fields at which they resonate for this particular frequency that you're used to measure, you can judge what radicals you have there, what is the structure of your material, and you can analyze that. So chemists, biologists use this technique a lot to analyze that. In my laboratory, I use that as an electron paramagnetic resonance, but at the same time, you can use the same equipment to measure ferromagnetic resonances, where you would be measuring magnetization oscillations. So if you have magnetic moment, it oscillates left and right, and all of them actually in a big material, all of them oscillate. So based on these oscillations, let me scroll back to the ferromagnetic resonance. For example, this is your material. So if you measure the frequency at a given field, we can extract the magnetization. So we can extract magnetization. More than that, in real life, this is lossless. So there are no losses. It's just Landau-Lifshitz equation. Now, if you go back to Landau-Lifshitz equation, this is our dm/dt. That would become m cross b vectors. So there are no losses, which means that magnetization will oscillate forever. But there are losses related to spin orbit interaction, and there are spin relaxation times. So we can add another term here, and it might seem to be a bit more complex. Ms than m cross m cross H. So this equation, I'm not going into the detail of where we get this, but uh, basically what we can get is a term here on the right that has this double cross product, and this is a damping constant, or it can be written in a different way. So what I will do, I will write it with a different color. So it's this one part plus a simpler form alpha divided by saturation magnetization. Oh, H, that should be B, or I should put M, no, not. So alpha M cross dm dt, which is the same. You see, m cross b is our dm dt in lossless equation. So this term is responsible for damping. And this is called, this was introduced by Gilbert to Landau-Lifshitz equation, and the equation with damping term, so that's dm dt is equal to gamma m cross b plus alpha over ms m cross dm dt. This is called Landau-Lifshitz-Gilbert equation. And in this case, if you have magnetization, it in Landau-Lifshitz equation it would oscillate forever along the magnetic field. In this case, if you introduce damping, what would happen? It would start to spiral down because we lose energy. We have this alpha here. Alpha is called a damping constant. So that is a more realistic model. And of course, if you want your magnetization to keep precessing, you have to add energy to that. That's why we need that small magnetic field and to add damping. And that is why the ferromagnetic resonance, if you measure chi as a function of frequency, it will be not just a single line, but it would be a peak which would have a certain line width. So line width is indicative of damping. Bigger the damping, more damping you put in that, wider the line width. Smaller damping, more narrow line width you have. And by measuring the ferromagnetic resonance of material, by measuring in this setup ferromagnetic resonance, you can judge, first of all, you can judge about the saturation magnetization. I can point it out here. So you have M, M, M there. So you can judge about the magnetization, but also you can extract parameters like damping, and you can say whether your material is nice and crystalline, how many defects are there, well, not how many, but how defective it is, and basically analyze the material. That is what it is used for in, let's say, magnetics laboratories. All right, this is the last lecture on magnetization dynamics. And the next lecture I will talk about, if I scroll upward, you will see that I plan to talk about spin torque. So that would be one of the topics of the next and the last lecture. And also in the next lecture, we'll talk about spintronics applications, and spin torque device would be one type of these applications and devices. All right.